We are now branching into the sound part of our waves and sound unit. So we spent a lot of time talking about mechanical waves, and now we're going to specifically talk about sound waves. And keep in mind all along that sound is a longitudinal wave, even though it might output to us in different forms, like on an oscilloscope as crests and troughs, and it'll look like a transverse wave. It's made up, it's a compressional wave. So that means it's made up of compressions and rarefactions, where the molecules are really close together in the compressions and really spread out in the rarefactions. Similarly to crests and troughs, right? Same kind of idea. The molecules or the particles in the medium are vibrating, and the propagation of the wave is actually parallel to the way that the molecules and particles vibrate. So don't forget, it's a longitudinal wave. You don't want to miss that. Okay, in order to have sound, we must have three things. The first one is a vibration, which could be like your vocal cords, so it's coming out of your larynx and causing that vibration actually allows us to have verbal speech. A tuning fork, a reed, strings, an earthquake, anything that makes sound would actually be the vibration. So anything that allow that vibration to happen will be kind of that producer of the sound. We also need a medium, really, really important here. A medium can be air, water, ground, like earth, solids, liquids, gases, anything that has particles or molecules in them. It cannot be, dum, dum, dum. Let's do this one. Not space. Not space. That's so fun. One more time. Not space. Waves cannot move through space. Okay. We also need to have a third thing, a receiver, which can be like your ear or a microphone, anything that can receive the input and do something with it, right? And your ear does something with it. We're going to talk specifically about what our ear does, how it helps to funnel the information to the right parts of our inner ear that allow us to deliver a signal to our brains, and our brains process what the signal actually is. It's really quite amazing. Microphones are another thing that will receive the information and then can do something with it. So you need to have all of those three things to say that we've got sound. The frequency, the audible frequency, so what we can actually hear, depends on the receiver and the mechanics of the receiver, right? And there's a reason that we have a certain audible range, and we're going to test this out in class. So hopefully it won't get like super tricky for anybody, but we're going to test this out in class about how our range can actually change depending on our situation and how old we are, stuff like that, right? So the humans can hear typically anywhere from 20 hertz to the upper limit seems to be around 20,000, but these are just, of course, averages and not necessarily guarantees. Dogs can hear 15 hertz and upwards of 50,000. So you can think of like a dog whistle that we would use to call a dog. We can't hear when we blow on it to cause the vibration. We can't hear it because it's actually out of our audible range. You can't hear above that 20,000 hertz, and dogs can. So really kind of super cool. Bats and moths and dolphins, they all are above 100,000 hertz. And they're using something called sonar. Put that down over here maybe. Sonar to hear. Meant to move it. Echo location. There we go. Any frequencies that are below our audible range of 20 hertz, we call that infrasonic. So it's below infrasonic is the name that it gets. Frequencies that are above 20,000 hertz are called ultrasonic. And you've heard that term before. I'm sure probably lots of you have even had an ultrasound, right? That actually uses sound waves to give us information. Isn't that, it's amazing, right? We can use sound waves that will actually give us information so we can see what's happening inside the body. So that's been used to give us body images. Ultrasonic waves have been used to actually break gallstones instead of having to do gallbladder surgery and get at the gallstones. If they're small enough, we can actually use ultrasonic waves to break them up. And it's even been used to heal tissue as well. Probably some of you had some physiotherapy that have involved using some ultrasonic waves to help you in your recuperation. So lots of amazing uses of ultrasonic. The frequency of sound is often described as the pitch, and that's not going to be a surprise. Pitch is a term that a lot of people use to describe frequency without even realize that they're describing it, right? So they'll say something is high pitched or low pitched. The high pitch to us as physicists means high frequency. Low pitch would mean low frequency. And we'll get some good examples of what that actually looks like. So hopefully this diagram came through on your stuff. I think you can get an idea of examples of what looks like infrasonic and ultrasonic and stuff that's actually in our range. So the first thing that it mentions, this picture here, is an acoustic microscope, and it can actually detect defects in certain materials. And look at how out of our range, that's 75 megahertz. So that would mean, with that mega there, that is 75 times 10 to the 6 hertz. That's what that means. Wow, like that's way out of our range. That's 75 million hertz. Ultrasounds are at 5 megahertz, so the same thing you can do with that mega. Let's really recognize what mega really means here. It's 5 times 10 to the 6, so you can replace the mega with a 10 to the 6. With ultrasounds, we get some pretty amazing imagery in utero of fetuses. So really, really cool, because it can give us some early detection possibilities, and sometimes this is really, really key for how the baby will be treated, especially when they're born. Say if they have a heart defect, and we can detect that early on by using the appropriate ultrasound, there's a chance that physicians can actually do surgery, in utero surgery, and operate on the baby inside the mother before they're actually born. Because the best thing to do is have the baby stay in utero as long as possible, right? Well, I mean, to the 9-month mark, not forever and ever, obviously. But yeah, it's really, really cool to see that this kind of identification can help us, that early identification can really help us make a difference of correcting anything that we possibly can, any defect that could be structural, that might be life-saving and has to be done in utero. So really, really cool functionality of how it's changed things over time. Fish finders can locate fish, and they are operating at 200 kilohertz, which is 200,000 hertz. Long-range military sonar may affect marine life. So there's a possibility that the sonar that we're using, because marine life can interpret it, they can actually feel that vibration, right? So that means something to them. So even at 500 hertz, that can actually have an effect on marine life, of course. And infrasonic vibration detectors, they're at 5 hertz. So this is where we're not going to hear that. That's not in our audible range. Anything like a volcano or earthquake, avalanches, nuclear explosions are all out of our audible range, but infrasonic vibration detectors could actually pick them up. So just kind of gives you an idea of what the range actually looks like, right? Oh, great diagram to remind us that sound is a longitudinal wave. What we've got here is a tuning fork. We've got a couple of these in class too. So we've got a tuning fork situation here, and I will show you some resonance using some tuning forks tomorrow. What we're looking at here is that once the prongs come together, they'll compress or hit the nearby molecules, and you'll get a compression that forms right in between the two prongs, where we get a rarefaction that kind of looks like the molecules are stretched out. But then once the prongs are spreading apart, you get a rarefaction in between and a compression just out on the outer side of the prongs. And that gives an alternating pattern, just like we would have seen with crests and troughs of compression, rarefaction, right? That just like the crests and troughs, right? Like you can imagine almost like this is crest, trough, crest, trough, crest, trough, or vice versa. I just randomly picked crest to go with compressions there. Okay, so that this is how the sound is actually going to propagate, because these molecules right here that are now in a compression are going to hit their nearby molecules, and they'll cause them to start to oscillate, and those are going to hit their nearby molecules and cause them to start to oscillate. And the just continues. There's multiple collisions going on as sound is propagating through, as the energy is actually transferred from the source all along as the wave propagates through. Okay, so really great example here, and good kind of visual of how sound can be a longitudinal wave, and that we can visualize that by looking at something as simple as a tuning fork. So we've got some tuning forks at school, and we'll try playing around with those, because they're at different frequencies, and it gives us an idea of what's required to have those different frequencies when you're using tuning forks. And we've also got a case where we can show some resonance too, which is really, really cool. So I will do that with you tomorrow, show you the resonance with tuning forks. Characteristics of sound. Okay, this is really, let me make sure I'm okay here. Yep. Okay, so what we like to think of with the characteristics of sound is that we can perceive sound as loud or quiet, obviously, loud and quiet, and that would be reflective of the amplitude that would output. See, look at this output. That looks like a transverse wave, right? Looks like crests and troughs to me. I don't know about you, but I'm thinking crests and troughs. You just told me it's a longitudinal wave. What is going on? This is the way that sound outputs. It's nothing to worry about. It's still a longitudinal wave, so please keep that in mind. It's still a longitudinal wave, but it's outputting as crests and troughs. Okay, and we talked about this earlier too. So it's going to output like that, and that's quite all right. The amplitude, that's the energy that would be indicative of the amount of energy the particles have that are in that compression or rarefaction, right? So if we've got a loud sound, we would have large amplitude. And if we were if we were perfectly quiet, it would be completely flat, right? You have destructive interference almost situation, right? That's what you want to think of with quiet. But quiet things will have a small amplitude because they're really quiet. Yeah. Okay, pitch is related to frequency. High pitch means high frequency. Do, 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 do. Look at how frequent that wave is. There's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 crests. I'm going to air quote that, crests, because it looks like it's a crest, but remember, sound is a longitudinal wave. And then a low pitch, or a not so frequent wave, only 3 crests. Let's air quote that. 3 crests, it's a longitudinal wave, but it's less frequent in this situation. And that means that it's a low pitch. And that's the kind of terminology that people who don't do any physics will understand. If you say the word pitch, they'll kind of have an understanding of what that actually refers to. The quality can be pure, just nice, usual, where you've got this kind of simple waveform that's, looks like our nice crests and troughs and everything's good. It can be rich, and it can be complex. Complex would mean it's like got made up of a whole bunch of other stuff. It could be crests upon crests and troughs upon troughs kind of thing. And again, remember, sound's a longitudinal wave. This is just the way it's outputting. Okay? And sound will also interfere. Whoa, that's good, because we said interference. Yo, we said interference was one of the characteristics of waves. So if sound is truly a wave, it better interfere. Look at this. This part here is the interference. Interference. Did I spell that right? Interference of the two waves above. So interference, that's really, really important. Sound waves will also interfere. So if we add the green one here with the blue one, the superposition or the interference pattern that would result between these two. Good gravy, sorry, hang on. Okay, don't worry. I think Reebok is okay. The interference pattern that would result between these two would give us a kind of superposition of the two waves, right? So you'd be adding the crest with the crest, but they're not happening necessarily at the same time. So we might get more of a complex waveform as the result. Depends how these two get lined up, of course. And if you had to do this, I would give you grid paper so that you could add those up nicely, right? Because that makes it so much more easy if we've got the grid paper and we can do that nicely. The key thing here for you to notice is that sound interferes just like our mechanical waves that we talked about earlier. And of course, sound will also resonate as well. And that's, we talked about some resonance possibilities yesterday. Of course, sound is a possibility for resonance as well. Okay. Anytime the vibration is meeting the natural frequency of the object, it doesn't matter if it's a sound wave or a mechanical wave, you can still have resonance. Okay. We're just going to skip just ahead here to lesson 8 and do sound intensity right now because it's just really quick and easy and straightforward. Sound intensity is kind of our loudness amount, right? Sound intensity is actually referring to how loud things are. It's really difficult to measure because the amount of energy involved is small in comparison with other forms of energy, right? Other forms of energy that you're used to. And because the potential range of intensity is actually really, really large. So the sounds with very tiny pressure difference between compression and rarefactions can actually be detected. The softest sound audible to humans has a formula that is, it's called intensity, and it has a formula of power, just like the power you know before, like it's measured in watts over a unit of area. So we would say intensity, capital I, is equal to P over area. And that P is power, and that A is area. The softest sound would be 0 decibels. The unit for intensity is measured in decibels, and that is named after our favorite telephone guy in Canada, Alexander Graham Bell. Ooh, cool, eh? The decibel scale is actually a logarithmic scale. So it's a base 10, kind of like the pH scale is logarithmic, right? So it's a base 10 scale. This is not a unit that you're responsible for here. The Bell conversion into a decibel, you don't have to be responsible for that. But just for those of us who are out there wondering how we actually get from decibels to bells, this is how it's done. Capital B for Bell is 10 picowatts per meter squared, and that's actually coming from your intensity formula. See how small that is? Like a picowatt? That's super tiny, right? A decibel is 1 dB, so we use small d, capital B, and that's equal to 0.1 Bell. Just for those who care, you're not going to really use that unit. We're just going to pay attention to the intensity of how this actually looks for us, and how the intensity can actually do some significant damage on human hearing over time. So that's why it's like dangerous to live near airports and stuff, right? Because if you're really, really close and you're constantly hearing stuff that has high sound intensity, like an airplane takeoff has huge high sound intensity, right? If it's got a high intensity, then that can actually be really damaging for our eardrum. So let's take a look at what the intensity is like and what that scale actually looks like. And I did say it was logarithmic, so you can actually see when we're logarithmic base 10, we're increasing by factors of 10, or like 10 to the n, like 10 to the 2 or 10 to the 3. It's the factor that we're increasing by. So it's a logarithmic scale. If the intensity is 10 times greater, the sound will actually be 10 decibels. 100 times greater would be 20 decibels, similar to like how pH scale works. 1,000,000 times greater is 60 decibels, and that's actually what normal conversation would be at. And what we're saying greater than the base, right? So we started off with this decibel base. 10 times greater would be 10 decibels. And then we could move up from there. That may have not been very clear. When I'm saying greater, I mean greater than this. Okay? Normal conversation, like I said, is 1,000,000 times greater than our start, which is 60 decibels. And that's because there's 6 zeros there, right? Like that's like a 10 to the 6, just like the pH scale. That's how the intensity works. 10 to the 11 is 110 decibels, and this is like frequent concert levels. And long exposure to this kind of volume and this kind of intensity is really, really dangerous over time, especially as you age. So it seems to be a little bit more significant as you age, and that's because your hearing is actually part of your nervous system, and we know that our neurons don't generate as frequently as other types of cells in our body. 130 decibels is enough to cause pain, and that will be significant pain in your ear. And if you can remember having an earache as a child, sound would have made you feel worse. Like think back to those moments when you had ear pain or an ear infection. Sound would have made it worse. When you have that kind of pain or infection in your ear already, hearing sound makes it worse because it amplifies the intensity. 160 decibels would actually shatter your eardrum, and that's coming from something like a space rocket. The intensity of sound is 1 over d squared. You can measure it, the distance from the source. So the intensity of the sound received by the ear actually depends on the power of the source and the distance between the source and the person. So that's why, we don't really feel the effects of any of the airplanes taking off at the Breslau airport, because our distance matters. It's that same kind of factor, that 1 over d squared, that distance matters. As we increase the distance, it really is going to decrease the intensity drastically. The intensity of the sound will decrease as the wave moves from the source to the receiver. Okay? So super straightforward. We just need to kind of be aware of it, be aware of what the intensity is. We're going to try a couple of homework questions as we play with this formula, but just recognizing that intensity, it's important for us to be aware of it as physicists, because we want to make sure that we are not creating something that would cause loud enough vibrations that could do some significant damage to the people living in an area, where they could end up with ruptured eardrums and complications because the sound is actually too intense. That is it for now. Thanks, everybody. And we will be on to the speed of sound for lesson 7 for tomorrow. Have a great day.